Now, the second derivative test for local max or min, so local extreme values. Theorem 5. Second derivative test for local extreme values. Suppose f double prime is continuous on an open interval. Okay, we have an open interval containing x equal to c. So as you can see, we use the x equal to c to mean a critical number. If f prime is at c is 0 and f double prime at c is negative, then what do we have? We have a line tangent to the curve that's horizontal, and then we have a concave down situation here because f double prime at c is negative, so you see that it's concave down. Then we have what? A local max occurring at x equal to c. Now, what about this? We have that f prime at c is 0. You see, it's again, you have a line tangent to the curve that's horizontal. Now, what else? If we plug in c into the second derivative and we see that the sign is positive, then we have a concavity that is concave up because it holds water, so that's why f therefore would have a local minimum at x equal to c. Now, if we have f prime of c equal to 0 and f double prime at c is equal to 0 as well, then the test fails. So in that case, the function may have a local max or min, or maybe not. So this is in a way an easier method of finding out whether at x equal to c you have a local max or min instead of using the change of sign of f prime. Here we just do it once. We just take the critical number for a local max or min, and then we just plug it into the second derivative, and if it's negative, it spills water, so you have a mountaintop, so that gives us a local max. And then if it's positive in second derivative, when you plug in the critical number and you have a horizontal line tangent to the curve, then indeed you've got a valley or something that holds water, which means you have a local minimum. Now I think we are ready to do some graphing. So if we've got a function in general, say, you're just given a function, and how do you graph it? All right, so here are just a few steps on how you can graph a function. First of all, identify the domain of f and see if there's any symmetry. Because if it's symmetric about the y-axis, that means you have a mirroring image about the y-axis. Okay, just something like that. So what about then you take the first and the second derivative. When you set the first derivative to 0, you get critical points for local max or min. When you take the second derivative to 0, set it equal to 0, you have a possible point of inflection. So find the critical points, okay? And then identify the behavior of the function at each critical point. Now next, find where the curve is increasing and where it's decreasing. Then find the points of inflection, like I said, based on the second derivative. And if you might have a vertical asymptote, a horizontal asymptote, or an oblique asymptote, depending on what kind of function you have. And most of the time, number 6, it occurs when you have a rational function. Okay? And then plot key points like the x and the y intercepts and also plot all the local the critical points that you have found from step 2. So let's see if we can try using these methods. But first of all, let's just go back and review what are the common graphs. Okay, you have a linear function. It has a negative slope. You have a cubic, which means this could also be x. It's the general shape of any x raised to an odd power. So it could be x to the 3rd, x to the 5th, x to the 7th, etc. And this is just a negative reflection. So if you put a negative in front, it'll just be reflected about the horizontal axis. So it'll just behave this way. Okay, and then you have quadratic, where y is equal to x squared. So it could also represent y is equal to x to the 4th, y is equal to x to the 6th. In other words, whenever the power is even, then the general shape looks like this. And that's just the negative of x squared, so when your parabola opens downward. Remember that this means that you square x first, then you take its negative. Alright, so make sure this is clear. That after you've squared that number, whether it's positive or negative, then you take its negative. Okay, and here you have an example of an inverse function, 1 over x, and that's how the graph looks like. And its negative would be reflected in the about the x-axis. Now, this would also represent 1 over x cubed, 1 over x to the 5th, so any odd power of x. And the same thing here. Now, here would be a representative of 1 over x to an even power, not just x squared. It would be 1 over x to the 4th, 1 over x to the 6th, and so on. And of course, if you take the negative of this graph, then it's reflected in the opposite direction. It's reflected about the x-axis. Now, here we've just looked at this. It's the cube root function, but this is a representative, I guess, if you call it that way, a generic function for the odd root of x. So it could be the 5th root, 7th root, 9th root, etc. And that's just the negative of it. And here you can have x to the 1/2 or square root, or you can also have the 4th root, the 6th root, or any even root of x. And that's just its negative. Again, it's the negative of this function. Now notice here that what is the domain of a square root function, any even root? Remember, if we're talking about real numbers, then the radicand will always be greater than or equal to 0. So the domain of this function is from 0 to plus positive infinity, which includes 0. As compared to when you have an odd root of x, then it's all real numbers because we can always take the odd root of a negative number. But here we cannot take the even root of a negative number of x. Okay, and then our famous absolute value of x, its negative counterpart, and here you have the greatest integer function and the least integer function. Now, it's good to have all of these functions in mind. That way, when you're in your graph, when you're graphing a polynomial or any kind of function, it will give you already an intuition of what could be the behavior of the general shape of your function. Okay, now one other thing that we can look at are intercepts. If c is a simple 0, which means that if you have a function where x minus c is a factor, like x minus 1, x minus 3, so you have a polynomial function. This is actually a quadratic function, right? Because it's when you FOIL that, you have y is equal to x squared minus 4x plus 3. So when you just have a simple 0, that means there's no other power here except 1 and 1 here. Alright, so what happens is f just crosses through the x-axis at the x-intercept or at the 0, and we'll just cross it just like that. Just like a line would cross the x-axis. Now, if we have c, it's a 0, but it has odd multiplicity. Let's say x minus 5, so 5 is the number right here, 5, 0, okay? And it has an odd multiplicity, 3, 5, 7, etc. Then what happens is the graph crosses through the x-axis. The graph passes through the x-axis but is flattened at the intercept right there. So instead of just crossing it that way, it eases and flattens out and then goes up there. Right now, if c is a 0 of even multiplicity, like, you know, if it's a squared, 4th, or 6th power, and so on, then the graph of f is tangent to or touches the x-axis at the intercept, at the 0. So let's say x to the 4th or x minus 2 to the 4th. This is what's happening. It either stays above or below the x-axis at the 0 or at the intercept. They all mean the same thing. A 0 and an x-intercept, they refer to the same thing. Now the general shape of x to the n, like we've seen a while ago, if you have just a line, if you have a cubed function, that means if it's odd, see how the higher the multiplicity, the flatter it is on a 0. On a 0. Okay? And remember that these zeros that are occurring at the origin, they can be translated to the right or to the left. Now, if you have even, see how these are all even, then it's either going to stay above the x-axis, and if it's negative, then it'll go below the x-axis. So the higher your multiplicity, then the flatter it is on an x-intercept. Sketch the graph of y equal to x to the 4th minus 4x cubed plus 10. Now what you look at is the leading term. If the leading term is x to the 4th, then what is the general shape? Okay, the general basic graph would be, it's sort of a quadratic, but it's just flatter at 0 here. So it will look like, the general shape would look like this, right? Okay, but then something happens because of the additional term minus 4x cubed plus 10. That's where we will encounter either a local max or a local min or a point of inflection. So what do? We take, so first let's determine the domain. The domain is all real numbers. Okay, in other words, we're not going to find any vertical asymptote in this case. Now, let's take, therefore, so that's the general shape, and we'll just find out what happens to this graph of y equal to x to the 4th minus 4x cubed plus 10. So let's take the first derivative and find out the critical points, if there are any. Right? First derivative is 4x cubed minus 12x squared, right? Plus 0, of course. And then you set that equal to 0, and we can see that 4x squared goes into both of these, so it's a common factor. So pull that out, and you're left with factored out in from x minus 3. And so set each to 0, and we see that x equal to 0 and x equal to 3 are your critical values. Now, what are these critical values? These are the critical values or critical numbers for possible local max or min. Does that mean it will automatically will have a local max and min on these 2 points? No, we don't know. Okay, so how do we find out? We can first use the second derivative test. That way we can, and if the second derivative test fails, then we use the first derivative test. Okay, test for local max or min using the second derivative test means you take the second derivative. Alright, so what's the second derivative? It's 12x squared minus 24x, right? Okay, because you're just taking the derivative of the first to get the second derivative. Then you take that critical number 0, plug it in here. But look, if we plug it in here, what happens? It's 0. So it's inconclusive using the second derivative test. So we can't use, there's no conclusion as far as x equal to 0, whether it's a local max or min. Now let's test. Y double prime at 3. So y double prime at 3, right? At y double prime at 3, that's 12 times 9 minus 24 times 3. You get 36, which is positive. Therefore, there is a local minimum at x equal to 3 because what do you have? You have a line tangent to the curve, Okay, that's with a slope of 0. And then you have a positive, so you have a concave up, and that's why you have a local minimum occurring at x equal to 3. But at 0, it's inconclusive. So what do we do? Then we'll just have to resort to the first derivative test. Okay, let's look at 0. And let's go ahead and plot 3 here. Even we already know that we have a local minimum occurring there. We just have to test the sign of y prime. So take 2 points. So our test point to the left of 0 would be -1. Our test point to the right of 0 would be 1. Alright, so if there is a change of sign in the first derivative, then we can conclude that this is a local max or min. So what is y prime at -1? So we plug in -1 in here. That makes it negative. So negative minus 12 times, that's already squared. So it'll be just have the same value, 12. So you've got -4 minus 12. That's negative. So you have y prime is negative when you plug in -1 into the first derivative. Okay? So it's negative, that means it's decreasing. So if this is a local min, you have to have an increasing slope or a positive slope to the right of 0. Well, let's see. So what is y prime at 1? So we plug in 1 in here, so that becomes 4 minus 12 times 1. So it's still negative. So there is no change of sign, which means that at x equal to 0, this is not a local max or min. It's neither. Okay? But we've already shown that at x equal to 3, you have a concave up, so we know that it will be increasing to the right of 3. Right, so what is our conclusion therefore? At x equal to 0 and the y value is 10, it is not a local max or min. So that means it's not a local extreme value. But at x equal to 3, you plug in 3 into where? The original function, and you get the y value equal to -17. That is a local minimum because we know from the second derivative test that it's concave up. With having concave up, it holds water, so you have a local minimum. Now let's find the points of inflection. And what do we do with this points of inflection? We set the second derivative to 0. So when you take the second derivative to 0, 12x is a common factor, so pull it out. So we have 12x times x minus 2. So when we set each factor to 0, we see that x equal to 0 and x equal to 2 are possible points of inflection. Right now they're critical numbers. So how do we know? Well, we just take the number line again. Okay, and here is 0 and here is 2. Okay, and we take points to the left of 0, so we use -1, and to the right of 0 we use 1, and then I will use 3 here because we already know the sign of the second derivative there. Okay, so y double prime of -1 is what? That's going to be 12 times -1 squared, which means it's positive 12, minus 24 times -1 will give us positive. So this is positive, y prime is positive. We have a concave up occurring. Now what about y double prime at 1? So that will just be 12 times 1 minus 24 times 1, which makes this whole thing negative. So here you're positive, here you're negative, which tells us that x equal to 0 is a point of inflection because it changed concavity from concave up to concave down. And we know already that at 3, y double prime is positive, so you have a concave up occurring to the right of 2. So also x equal to 2 is a point of inflection because it changed from negative to positive. So we have 2 points of inflection at x equal to 0 and at x equal to 2. Now let's look at all the critical points. You have the critical point for point of inflection, and then the critical point for local min. And you see how you have a concave up and then concave down. From 0 to 2, it's concave down. And then 2 onwards, from 2 to infinity, it's concave up. So combine the concavity being positive concave up at the same time having a horizontal line tangent to the curve. That's how we acquired a local minimum. Now the question, does this have an absolute minimum? Yes, because this is going to go to plus infinity, and that's also going to go to plus infinity. It does have a local, at this point, because we're just concentrating on this area, this local minimum now becomes an absolute maximum for the whole graph of the function. So what did we look at? First, the basic graph was an x to the 4th. Then we looked at the critical values. I'm just, summarizing what we did. Okay, and then we used the second derivative test for the local max or min. After that, if the second derivative test fails, use the first derivative test. Then critical values for points of inflection means we set the second derivative to 0, get the critical numbers there, and use second derivative test for concavity. And then find the critical points by plotting them. And that'll give you an idea, and additional points if necessary, just to help you graph it. Okay, so we have now graphed x equal to f of x equal to x to the 4th minus 4x cubed plus 10. So if you go to your ebook, this is example 7 if you want to read your ebook.